Welcome to the session on SD-WAN architecture. My name's Ali Sheikh. I'm a technical leader with the Enterprise Networking Group. Today with me, we have Zain Mirza, a technical marketing engineer with the SD-WAN group. Hi, Zain.
Hi, how are you doing?
Doing well. And today we also have David Klebanov, a TME solutions leader, who's going to be with us as well. Hi, David.
Hi, Ali. Thank you.
Today's presentation is going to look into the evolution of the SD-WAN solution. That is, from classical networking components to the SD-WAN technology as we have it today. Presenting for us is Vinay Prabhu, a technical leader in the SD-WAN space. Vinay?
Thanks, Ali. So let me get on with it, where I'm going to talk about the timeline. We'll go back in time, see what the traditional routing architecture was and how it maps to the current SD-WAN solution. So as most of you are familiar with the traditional router, this is a sample router. It's a Cisco 7600 series router. Sits on most of the customer edges or provider edges. But essentially, this architecture is what ran the internet for the past 15 or 20 years. It's this, the same architecture that is followed for your access point that resides in your home, inside the core routers in your service provider network. So what was this architecture? How did it look and how did it function? It consists of three main components. Let's mark them out. So as you can see, you have the I/O module, the control plane module, both of which are pluggable modules in this case, which reside on a chassis and are interconnected using a backplane, the switch fabric. So this is a physical connection of pins that actually connects these two pluggable modules, the I/O and the control plane module. So what are the functions of each of these three components and how they map to the SD-WAN architecture? So to get into the functions of these, we need to understand a couple of things. The types of packets in a network. You have the routing packets and the routed packets. So what is the difference? The routing packet essentially carries information about the different endpoints in your network, which help in building up a table on each of these routers. The routed packet is basically all the payload, the actual data that we want to transfer from end to end in the internet. So where do these packets live? Where do they enter the box, and how are they handled is what we'll go into next. So both the routing and the routed packets actually enter the I/O module. These physical ports that you can see in this diagram are the physical ports which are connected to cables that essentially connect it to some other router as well. So packets live on this network, traveling from one box to the other box through this cable into these ports. These ports, again, are on the I/O module. The I/O module could receive two types of packets, either the routing packet or the routed packet. The routing packet, let's basically split this into two workflows. A routing packet enters one of these ports. The routing packet essentially is carrying information about networks and how they can be reached. This information is what the router actually needs to build up a routing information base. So what the I/O module does is just punch this packet up to the CPU saying, hey, I've got this routing packet. It has some information which might help you actually create a routing table. can you help me out with this? How is this packet punted to the CPU module? It's using the switch fabric. Okay, so any communication that's going to happen between any of these components or within any of between the same components is going to go over the switch fabric. So you'd want to actually remember that, because that's what SD-WAN is also going to leverage. So what happens is this routing packet makes it into the I/O over the switch fabric onto the CPU.
Hey, Vinay.
Yeah.
Can you give us an example of what the routing packet is?
Example of any routing packet could be any protocol like OSPF, BGP, anything that's helping you build your routing table across the network. So each of them would have some information about their neighbors and what the neighbors can bring for you. What kind of reachability does your neighbor have? So this packet basically carries information which is punted to the CPU. The CPU then builds up a table of routes called the routing information base. This is an unpruned routing table. It basically has all the possible routes that this box has received from the network. We can further optimize this to get rid of duplicates or perform any sort of policy actions on this routing table to create a concise view of the network, which is called the forwarding information base, or the FIB. This FIB is the table that's then programmed back into these I/O modules. So the I/O contains the FIB. Okay. So what does the I/O module do with this FIB? So remember the second type of packet, the routed packet. This is the actual data that you want to transfer from one end of the network to the other end. So the routed packet makes it into the port on the I/O module. The I/O module refers to the FIB that was created before and determines what the next hop of this packet is supposed to be. Is it an endpoint that I can reach directly, or is it an endpoint that I need to get to another router to get to? So, any questions so far?
So Vinay, when we talk about this handing off the routed packet to the CPU, or sorry, the routing packet to the CPU,
yeah.
Does it not bring in concerns of CPU utilization and CPU constraints?
It is. So basically how fast, okay, so there are two aspects to traditional routing. So since each of these modules are separate physical modules, the network processor itself, there's a network processor that resides on these I/O modules too. So your forwarding performance, your throughput, all these values are a function of the I/O and not actually the CPU. The CPU is just working on the tables. So yes, the convergence times would be a factor. So how fast a network converges is a function of the CPU of the router. How fast you can switch packets through your network, basically transfer data through your network, is a function of the I/O. So each of these have network processors in them, but their functions are completely separated. So yeah, so generally you'll have redundancy on the controller itself, so that you can, the routing information is never lost at any given point, so that you don't black hole traffic. But the maximum amount of compute you want residing in the I/O more than the CPU in this architecture, because the actual throughput, the juice in the box, is determined by the I/O module. Hope that answers the question. So,
I had one question.
Yeah.
With regards to routed versus the routing packet, there's two distinct differences, and they all inherently go through the switch fabric. Can you explain those differences?
So
I guess you mean in a matter of priority.
Right, correct.
Oh, yeah. In a matter of priority, yes, the routing packets need to have a higher priority. You don't want to drop that information because that's the information you're relying on for switching the routed packets through your network. So in terms of priority, each of the vendors will have different queuing mechanisms between the control and the data plane. Routing traffic is also called control plane traffic, right? So control traffic, we call it as control traffic, will always have the highest priority as compared to routed traffic. Now, does that mean the performance of the box would degrade because of these priorities? No. You typically don't expect a lot of control plane traffic or routing traffic. These are just table updates. These are just routes, and once a network has typically converged, you're not going to get a lot of messages for which are going to reside in this bucket. So we give highest priority to routing traffic as compared to routed traffic. The messaging on the switch fabric is completely custom. So everything that gets in or out of this box has to be standardized, because you may or may not be the only vendor. Everything that resides in the box need not be standardized. So any messaging that goes between the I/O and the CPU, or between the I/Os or between the CPUs over the switch fabric can use any non-standard protocol or messaging system, because those messages have no relevance in the outside network. Okay. So let's see how SD-WAN came into being from this architecture. So SD-WAN is essentially the same 7600 router. There is no difference between SD-WAN and our traditional router. What SD-WAN brings is splitting these three components to build a network. So the I/O module we call the edges. This control plane module we call the controller or the smarts. And guess what the switch fabric is? It's the internet. So all that we did in SD-WAN was split this wide open, got the I/O on the edges, got the control plane module into the cloud on-prem, basically out of the box, and the communication between the I/O and the control plane was now a function of the internet. Could this not have been done earlier? Is this something out of the box? Not quite. It was just a function of when you trusted the internet. In the early 2000s, the communication between the I/O and the control over the internet would have been highly lossy, with large latencies, with fewer SLAs. Today's internet gives you a large amount of bandwidth, good SLAs, and a high amount of trust, such that you can split this open and still expect the control and the I/O module to be able to communicate with each other. The biggest advantage of a single box solution was that the switch fabric could be assumed to be lossless. It's all residing on the same box. There are not many messages going between these two. So this physical interconnect ensured that all messages between the control plane and the I/O were lossless. With today's internet, yes, we have a little bit of loss on average, but it's within tolerance such that you can distribute this architecture. So this is what SD-WAN is, just blowing this single box solution over the internet.
So Vinay, can you highlight what are the critical advantages of having done this at an architecture level, of taking the I/O to the edge and taking the control plane module to a controller?
Okay, that's a good question. So what are the advantages? So like I mentioned at the start, what was formed on the control plane module was your routing information base or your routing table. This was then eventually optimized and programmed on the I/O module. So forwarding table was what was programmed in the I/O module. Now imagine a network, or let's say our customer network, a 6,000 node network that is using this architecture. The routing table is a function of the chassis itself. So if I have 6,000 sites, there are 6,000 such boxes, and there are 6,000 such routing tables. These 6,000 routing tables then are programmed into each of these boxes, essentially. So any change in the network has to be propagated to 6,000 routing tables. What does it mean is managing a network that's large becomes cumbersome, because if I want to apply a policy, I want to withdraw some routes. Now I have to touch 6,000 routing tables individually to make that happen, because each of these boxes has its own view of the network. By splitting the architecture, what happens is I can have a limited number of control plane modules handling all the IOs in my network. So I could still have 6,000 IO modules and have only maybe 4 control plane modules. Now how many routing tables do I have? I have only 4 routing tables to manage a 6,000 node network. All I have to do is manage this routing table, make updates to this, apply policies, point my intent towards these 4 to have an effect on 6,000. That's one of the primary advantages that SD-WAN is going to bring to us when it comes to scale. There are more advantages. We can go over these, I think, in the next slide as well. But yeah, this is one of the big ticket items that SD-WAN solved for most of the large-scale networks that were present today.
I have a question. Now, you mentioned the switch fabric of SD-WAN is basically being replaced by internet transport.
Yes.
So what about those customers who don't necessarily rely 100% on internet and have this hybrid environments where they continue running internet alongside with their more traditional means of connectivity, such as MPLS, for example? Will that solution work?
Well, yeah, that solution will work. In fact, that solves a lot of their security concerns as well. So as I'll mention further down the line, that by switching our architecture in a certain fashion, which I'll mention, we can actually keep all our network secure by segmenting the network itself, the switch fabric itself, into a secure half and an unsecure half in terms of maintaining keys, how we exchange all of those, and how we exchange the routes themselves. So hold your thought, but yes, we can do both MPLS and internet. So the transport, essentially, it's transport agnostic. All we care is there's a switch fabric, there is a network that will help me talk to the control plane. So if we can talk over MPLS, we can do that. If you can talk over the internet, we'll use that.
So Vinay, when looking at this model and transitioning to SD-WAN, what is it that we lose?
Okay, so one, for a fact that we lose a lossless switch fabric. The lossless switch fabric is now replaced by a partly lossy internet, so the architecture has to account for the lossiness of the internet. It's not a problem we can't solve, it's just something that you have to account for. The second part is, by being physically present on the same box, each of these components knows the location of the other component. You don't have to program the CPU to tell it where the I/O module is. You don't have to program the I/O module to tell where the CPU is. It's all on this single box connected through a single switch fabric. So we lose sight of where all these components are when we open this architecture up. So you have to add another component into this architecture for it to actually work for an SD-WAN solution. So it just adds one more moving part in there, but we'll see how we tackle it. There are a bunch of things we can do when we add an orchestration component into this architecture. So let's move on to the architecture itself. So as you can see, if you remember the previous router, this is the same router right here. The I/O modules, we call the Viptela edges or the C edges, the Cisco edges. These can reside, as you can see, anywhere, the data campus, branches, remote sites, or in the cloud itself. So this is essentially the I/O modules that we saw in the previous architecture. The internet, like David, you had asked, the switch fabric itself is agnostic to what technology you're using. You could use MPLS, broadband, LTE. It doesn't really matter as long as the I/O can now talk to the CPU. We call the controllers, and we call them the vSmarts. There is an additional component here right on top. We call the vManage. We'll talk about it a little later. It's a powerful NMS platform or network management tool, which allows you to program your intent into the network and also get a feedback loop going in for the network operator, the network admin, to manage this entire architecture. So we'll punt the vManage for now. Like you asked, Ali, now the edges reside somewhere in the internet. The controllers reside somewhere in the internet. We need one additional component to actually let the edges and the controllers know where they reside, because now this is a chassis distributed over the internet. So we bring in one more component we call the vBond. Okay. So what a vBond essentially does is what a stun server does for getting a NAT mapping in today's technology. So it is essentially the one component in the Viptela architecture that is a server for everyone. Okay, so in the Viptela architecture, each of these components would act like a client or a server at some point for someone or the other. The vBond will always be your server. Everyone goes to the vBond. So if there's ever a doubt on what the vBond is, just treat it like any server, a call home server, a call home device to which everyone comes towards to get a view of who they should be going to.
So Vinay, would it be safe to say that device is for network discovery, similar to before where physically we knew everything was?
Yes.
Now we need to discover where everything is.
Exactly. So the vBond is used for discovery. So essentially when your network comes up, what you want is everyone to register with the vBond. This is the only component in the architecture that everyone should have reachability to. So this essentially resides in the public space. You would want it to reside on a publicly available network in order for everyone to have access to it. If you push this into the private cloud, you may or may not have access to it. If you don't have access to it, there's no way for an edge, an I/O, to know where the controller is.
So Vinay, you mentioned the trusted fabric and the three components from the controllers, vSmart, vManage, and the vEdge router. Can you explain how these three pieces authenticate to each other?
So we use a combination of whitelisting and certificates. I'll double click on it in a moment and I'll describe it in detail on the next slide itself. So we'll go ahead with what the vBond does. We call it the orchestrator. So you'll always hear this term called vBond as an orchestrator. The edges are called edges. The controllers are called vSmart. The NMS is the vManage.